morning, everyone. Welcome to What's the Difference for ICS in South Seas GH, just in case you not know where you are. We have Chris Sistrunk and Josh Triplett here to present. Should be an interesting talk. But before we begin, a couple of quick notes. The business hall in Bayside AV, that's where all the vendors are. Check them out, lots of good stuff. The Black Hat Arsenal is continuing in the Palm Foyer on level 3. And there's also an Arsenal reception this evening at 5 o'clock. Finally, if you haven't picked up your merchandise, today's your last day to visit the Black Hat Swag and Bookstore. Always lots of cool things down there. And finally, be sure to put your phones on vibrate so we don't interrupt the talk. All right, Chris?
Thanks, Dave. He does great work for all the speaker proctors. Do a lot of great work. I used to be one. So let's get right into this. What's the difference for control systems? We're going to give a little overview of DFIR. How many people in here have done DFIR before? All right, how many people have done digital forensics on embedded devices or control system type devices? All right. That's about what I expected, not very many people. We're going to talk about what to collect, what to analyze, and give some examples from substation devices, RTUs, from GE D20MX, and a Schweitzer Engineering Labs RTAC. And then Josh is going to talk about this tool that he's currently writing. We'll preview the part of it today about this VxWorks DFIR tool. We want to find evil in incident response. We want to see what's going on. And a lot of times you don't know what's going on inside devices. You have to look at all the different logs, see what kind of files and changes may be made. Irrational behavior. No telling what could be going on the device. We've got to look, see what's going on, give a triage, and have some kind of response. So for digital forensics, you're collecting files, volatile and non-volatile, memory from the operating system, network traffic, applications. All this stuff is from NIST and some, like a book, Incident Response and Computer Forensics. In regular DFIR tools, you've probably seen some of these red line volatility. There's cheat sheets and websites and books. But guess what? On the control system side, ICS and embedded devices, we don't really have that. So how is ICS affected? Assess the situation, that's same. And we have some other things that are the same, like communicate to management what's going on, and documenting the findings are similar. But, the physical processes are different than in IT devices compared to control system devices. We want to make sure the control system is returned back to a safe state. And the ICS devices have real-time operating systems and control system protocols that are not IT-centric. So we have to collect these manually. And the analysis has to be done by hand. There's no tools. Whenever you try to regain control of the control system, you don't just re-image the machine like you do with a Windows box. We might not be able to do that on control system devices. Most devices like that, embedded devices. An ICS anomaly, how do we know if it's an anomaly, and then what will we do to raise that to an incident in your incident response? An anomaly is occurred sometime, and we don't know. Maybe it's an increased network activity, a lot more bandwidth than you're normally seeing, strange behavior. If configure's on Windows XP HMI, it's going to be generating a lot of traffic, and you're going to notice that traffic. We need to investigate the anomaly. Is it known bad? Is it unknown bad? Is it just a known commodity malware like configure, or could it be just a misconfiguration? Do we escalate this? Who do we call? Do we call engineers and technicians to collect data? And if it's a big event, we might have to call PR and the law team and safety. And obviously your control system vendors, because they may have access to certain analysis parts of the control system devices that we may not as an engineer or a IT security professional. So in this instance, let's say we had a configuration. This is just an example. Someone put the wrong baud rate. So that's misconfiguration. Or you might have a squirrel that take out a power line, and we have to find that squirrel. It's dead in the substation. Okay, that's the forensics evidence there. Or we might find evidence of config or any other kind of commodity malware, or even targeted. We're starting to see a few of those coming out. As in regular DFIR, we don't want to lose the forensic evidence. How many times have you seen, if you have control systems, how many have seen logs being collected, and it's not very popular? Or, we've gotten a call at Mandiant where they had an incident on a control system, but they didn't collect any logs. So FBI can't really help out. We can't really help out. And if you turn it off and on again, you might lose all that stuff that's in memory and all that good stuff that we want to keep and preserve. So how do we collect this data from control system devices if there's no DFIR tools like volatility and redline capability? Well, we have to use the tools that we normally use in the control system world. So TerraTerm or any terminal server, PuTTY, Notepad, looking at configuration files, or you can use the software client. So there's the pictures of GE and Schweitzer's configuration files, and you got to connect to it with a serial cable. So we have to do a lot of these collection of data with existing tools. So for embedded devices, what do we collect? I'm going to break this down into two items. We have physical data and then digital data. Physical data is like the exact location of the device, which substation or what platform out in the Gulf of Mexico, you got an oil platform, or what breaker cabinet it might be in, device description, serial number, part number. What are the LEDs? Whenever I got a call and there was a problem in a substation, send the technician out and say, well, what do the lights say on the front? Are they red and blinking, or are they all green and acting normal? See what the power consumption is. Temperature. We had Mark Febro talked about an event where there was a Windows HMI in a combined cycle power plant that they noticed with the FLIR camera, one of the boxes was really hot compared to the others. And then they found out that it had malware on it. So you can use out-of-band ways to detect and collect information. And evidence of tampering. So physical access is important. You need to keep tabs of that as well. Digital data, running configuration, known good configurations. Is it approved firmware? Because a lot of times companies will have a set of approved firmware, and sometimes you'll see rogue firmware out there that might not be approved for the company. But someone went and downloaded it and installed it anyway. CPU usage percentage, memory usage percentage, things like that. Whatever active ports are listening, logs, and in more advanced cases, you can do a memory dump. The time it takes to do these collection and how to analyze these, there's things that are done fast and things that take a lot longer. So for first responders, these are the fast things. We want to get the user logs and the event logs. And so in an embedded device, you may have to connect with a console cable and look, and it may only have 255 messages before they roll over. So you have to get those logs quickly before they roll over. And in newer devices, they have more storage, so that may not be a problem. But again, a lot of these control system devices are out there 15, 20 years. Does the configuration match the firmware? Is the firmware approved from the factory acceptance test? Is it running a standard configuration that you're normally used to seeing? With the Aurora attack at INL, they changed the settings in the relays. And if they would have pulled the configurations from those relays, they would have noticed something was different. Again, same with the logic. Is the ladder logic correct? Is the all of these settings that you would normally see for that control system or that process correct? Are communications normal? Are you seeing normal traffic? Are you seeing strange traffic? Are you seeing something beaconing out where it's not supposed to be? And the things that's slower, you may have to analyze embedded control system, operating system files, capture data rests or packets from the Wireshark or TCP dump. Those take a lot longer to analyze, and it may take a week in some cases if you don't have a baseline. And you have to get really experts to really look at this information. And sometimes you have to get the vendors or someone that's an expert, say in VxWorks, to look at this. And same with volatile memory, looking for code injection or potential rootkits. So, for instance, let's say we have a engineer with a laptop and it's infected, and he plugs in serially. Well, that would allow a way to inject code over the serial port and inject it into memory in that device. It's very possible, and Josh, he'll talk about that in a minute. But we'll show with the tool how we can detect some of these things in memory. So let's do some DFIR on two popular substation RTUs that's used in North America and starting to be around the world. One from GE, one from Schweitzer. Time to read the manual. How many people like to read manuals? Well, these two devices have very good manuals. PowerQuick 2 Pro processor on this D20. It's got a gig of RAM. It's got VxWorks. And so there's, if any of you are familiar with Substation World, you're probably familiar with this device, and you probably have these manuals already. So this is for you, some information that you can use in case you need to do some forensics, if it's even if it's troubleshooting an actual configuration problem. You use the software, use the information from the D20 products, and terminal, WinSCP. Talks about how to troubleshoot in Chapter 11. Really nice to have. There's some shells that we're going to look at and some logs. So one of the things that we look at is the error log. When you log in, it tells you what errors there are. Well, that's really handy. I use that every day in my job. Someone put something wrong in the configuration. Well, the error log tells you what's wrong. And then event user log shows who logged in, what their commands were typed, and those all get dumped to syslog as well. So in the D20, there's 3 shells. So you can get to some of the shells, one shell remotely, but you have most power from physically there being at the console port. And the same thing with a lot of other control system devices. You have the most power at the console. A lot of these commands you may not be familiar with on a day-to-day basis, but the vendor may have some specific commands for you to run. So there's 3 shells. If you've watched the Demolition Man, he didn't know how to use the 3 shells. So there's a D20 shell, there's a C shell in VxWorks. If any of you are familiar with VxWorks, there's a C shell and a command shell. And all 3 of these are very, very important to use when you're collecting data, especially for forensics. D20M is the main shell. It's similar to a 68K monitor shell in older D20s. The incident responders want to collect data, and you can see a screenshot of so many different commands. You can look at all the different juicy commands, and for a responder, that's really great. Also an attacker, that's really great. You can see what's going on. And all the details for the shell commands are in the user guide. So we can get the running configuration. We can get the last known good configuration. Might be stored in a secure file share at work, at the power company, or say if you're at an oil and gas company, you might have a common place where you store your configurations. Or it might be on a USB stick, or it might be on a CD in the cabinet. And you can look at the you can look at the running firmware, you can look at the CPU usage, memory usage, and do a query on the process to see what running processes there are. Very handy. We can do data collection. Serial analyzer, how many people still use serial? Yeah. 1200 baud. So what's Wireshark? We can use serial analyzer to look at the traffic, and this is an example of using DMP3 over serial, so we can do forensics that way. We can capture serial traffic, and obviously you can capture network traffic with Wireshark or TCP dump. You can also dump memory. So that's really great. You can show the sensitive information, shows where the NVRAM starts, and that's what you want to look at, and the physical RAM, and it shows the addresses where you start to dump them. So I show in the command there D, and I start with the address 00, and I go to FFF, and then it just starts dumping it on the screen. Well, that's great, but it takes a long time over serial to dump a gig of RAM. It takes like 6 days. So yeah, 115, 200 baud. So what you have to do is figure out what parts of memory that you want to look at. C shell, same way. There's some very good, if you're familiar with VxWorks, there's some great tools in there, mainly used by GE for troubleshooting, but any other product, if it's Emerson, they use VxWorks. There's others that use VxWorks. Same process, same C shell, same command shell. You can do netstat, you can dump, you can look at the firewall, syslog, you can even save a PCAP on the device itself. So this is where we get into memory. So let's say I have an infected laptop, and I connect it to, this engineer connects it to the controller, and it injects in memory with the VxWorks C shell memory edit command M. So we put dead beef in there, and we collect the volatile memory out, and we see that it's dead beef. So this is not really a bad thing, but someone could inject maliciousness in there. So I'm going to turn it over to Josh so he can talk about this tool that he's been working on.
All right, so I'm a Windows reverse engineer. So if I'm being asked to look at ICS equipment, we have a really big issue. But so one of the biggest problems was we don't have tools that enable us to do DFIR on ICS, and we should probably have those. So the solution I came up with is we should be able to read and write to memory on a device programmatically. And we're going to have to add modules to enable us to do that on certain devices, but I wanted to start with something generic, so I picked a VxWorks device that I was able to talk to. We should be able to cache the live memory locally. We shouldn't be requesting a page twice, mostly because it takes 6 days to get a gig of memory. And we should be able to compare the system image to something that's actually good and that we know should actually be on the device. If our memory on the device, or if our image on the device is actually bad, that's a really good starting point to start looking somewhere else and try and find out where this originated. But if we can provide the ability to read and write and cache device data, we should be able to do that for other tools. And if we can provide that ability, it should be faster for tools to access memory because they can piggyback off data that other tools have already pulled. So cool features that we implemented are we can easily accommodate different transport mechanisms. So serial, TCP to serial data bridges, protocol specific to other dumping utilities. So if something is compiled natively for like a VxWorks device running PowerQuick 2 processor, and they're using a binary format, we can provide the ability to support that. Caching is extremely important, so we're not waiting 6 days to check if data is actually good. And we should be able to do comparative analysis on all the different types of objects that we can, provide other scripts. So cache files, memory dumps, sparse memory maps, special objects that request live memory. I use the latter the most, actually. As you can see in the picture there, I'm connected to the GE D20MX via a Raspberry Pi, and I've got very little processing power to do anything comparative. So I wrote a quick tool to demonstrate the ability of pulling live memory and caching it, and then validating that it's good. Basically, this creates a mock memory or a mock process memory space, and I'm able to iterate over every instruction in the text sections, all of the data. So as you can see, we've identified a routine that's been modified with, it's actually a return 0 at the beginning of IP firewall start. And so you can see the other sections matched, data mismatched, but that's because of live running memory. We've got sections that aren't even loaded into memory and we don't even care about whether they match or not. So basically, somebody disabled the firewall in this thing, and that's really bad for our security. So interesting projects that we used, CleLoads Everything. That is a fantastic project for providing a mock memory space, being able to load relocatable executables in the future, hopefully in the next 3 weeks. It identifies architecture, endianness, provides you a capstone disassembler object, and Capstone was great for being able to disassemble the PowerPC Big Endian 32-bit instructions. So our plans for the future, I should probably document what I did and then expand the tool to work on other devices besides VxWorks.
At QNX.
Yeah.
QNX
being able to support anything else would be great. And then moving the scripts from just being a trash bin of scripts into easy to use and easy to contribute to modules, and then hopefully open sourcing our code and moving the code to GitHub so that we can further this project along. And then I'm really looking for feedback, feature requests, bug submissions. I'd really like this to be something that's actually usable instead of something that I just burn time on. So I think that's all I have. I think going back to Chris.
Thanks, Josh. We're going to talk quickly about the RTAC. We've got just a few more minutes. RTAC is a real-time Linux, and it's also PowerPC related. It's got really great manuals, and you can get to it with a web browser in this case. Unfortunately, there's not a way to dump memory on this one, but we can still collect digital data, running configuration, user counts, CPU usage, memory usage, post checks, and we can run reports. There's also physically on the board, if there's a password jumper on these, so if you're locked out, you can put the password jumper, you physically have to be there. And that's another way for forensics. So if someone broke in, put in the password jumper, and then made some changes, that's a way we can detect that. So here's an example. I did some DMP3 research several years ago, and here's a screenshot whenever I send a malformed DMP3 packet. You can see it sent the CPU usage to 100%, and then eventually it watchdogged and rebooted. And then you can see the next slide, next picture shows the project failed, running failover project, and storage usage and storage available went to 0. Very interesting. You can see quickly with the different ports are being used, like there's some troubleshooting points that it stores in the tag database, and you can also look at syslog. Here's an example of an IED, Intelligent Electronic Device report, and you can access this with ODBC. Unfortunately, there's no Linux shell, so there's pros and cons with that. So Schweitzer really locked this down, but we can still collect forensics data. You can also capture Wireshark and Ethernet and serial traffic, and there's some good user guides from Schweitzer on this. And they also published several Wireshark dissectors for self-fast messaging protocol, which is used by all their Schweitzer relays, and Telegear 8979, which is a SCADA serial-only protocol that they can tunnel over TCP. For more further reading on, and you might want to take pictures of these, and I'll also publish the slides. H.D. Moore did some research with VxWorks, and he wrote a module memory dump for Metasploit. David Odell had a blog post on QNX, and ICS Cert has some recommended practices for ICS forensics. Travis Goodspeed did some really great work on embedded device work, MSP 430 family. Ralph Wagner did some really great Stuxnet work. If you've read his on, really got into the nuts and bolts of Stuxnet. And then most recently, the Ukrainian power grid attack. They attacked the embedded serial Ethernet converters and overwrote the firmware on those devices. So ISAC and SANS put out a defense use case document. So we probably don't have much time for questions, But you can come and find us later or out in the hallway. Thank you very much.